This is a 400-meter track. As of May 2025, the men's world record stands at 43.03 seconds. The straightway is 84.39 meters long, not 100 meters. Why such an oddly specific number? Let's math travel to the hidden science of the 400-meter track, from friction to centrifugal force. Don't forget to subscribe for the next stop. The 400-meter track is made up of 4 parts. The 2 curves together form a full circle. Lane 1 is the standard for 400 meters. L is the length of one straightway. R is the radius of the circle. The total track length becomes 2L plus 2 pi R. According to international standards, L is 84.39 meters. R is 36.5 meters. Plug those values into the formula. Oops, it doesn't exactly add up to 400 meters. When runners in lane 1 compete, they don't run exactly centered on the painted lane line. They run with the line on their left side. Because of that, the effective radius is slightly larger, about 36.8 meters. When we adjust for that, the total track length becomes exactly 400 meters. Why was 84.39 meters chosen for the straightway? First, the size and shape of the field inside the track. The infield isn't just empty space. It's used for other athletic events like shot put, high jump, or javelin. We need enough space for those activities. The infield area is the sum of a rectangle and a circle. When the straightway is 100 meters, the infield area works out to about 9,500 square meters. If the straightway is 84.39 meters, the infield area increases to about 10,500 square meters. It's larger. A bigger infield is better for hosting multiple events safely. But that's not the only consideration. When runners race through curves, they experience centrifugal force, a push outward due to their momentum. It slows them down and puts more strain on their bodies. Running curves is harder than running straightways. If the radius is small, runners have to make sharper and quicker turns, which increases the risk of injury. If the radius is large, the curve feels more like a gentle bend, making it safer and easier to maintain speed. Look at the data. The speed reduction rate varies depending on the radius. The larger the radius, the smaller the speed reduction. But increasing the radius shrinks the straightaways, meaning less distance for athletes to sprint at full speed, potentially worsening overall race times. The track must allow runners to be fast, but also safe. From a physics perspective, we can even calculate the minimum safe radius. When a runner's foot strikes the ground, friction is what keeps them from slipping outward. The friction formula is this. Mu is the coefficient of friction. M is mass. G is gravitational acceleration. The centrifugal force formula is this. To prevent slipping, the friction force must be greater than the centrifugal force. Simplify. R must be greater than this. Considering the world record for 400 meters, suppose the runner's average speed is about 10 meters per second. And sprinters wearing spike shoes typically achieve a friction coefficient between 0.8 and 1. The higher the coefficient, the less likely they are to slip. Let's use mu equals 0.8 for this calculation. The minimum safe radius comes out to about 13 meters. In that case, the straightway would stretch to about 159 meters, creating a long and narrow oval. The infield would be very small, and the risk of slipping would still remain. That's why we need a larger radius. Over time, through experience and refinement, the final standard settled at the radius of 36.5 meters. Each straightway is 84.39 meters. This specification is the beautiful result of precise math and careful design. Did you enjoy math traveling? Please subscribe for the next trip.